I'm the coordinator from the University of Roma La Sapienza. It's a Call 7 IP project, and these are the partners. There are 10 plus 2 third parties, and our team plays, if you're familiar with soccer, 4-4-2. So we are 4 research institutions, 4 universities, and 2 industrial partners, but we are also divided by countries, 3 countries, 4 partners from Germany, 4 from Italy, and 2 from France. I don't know if as coordinator, you have seen these recent diagrams. We place ourselves in this classification under Robotic Co-workers project, and our sector of interest is both industrial and professional service. So what is all about Safari? So this trip is intended to have co-workers working in real application, both of the industrial type and professional service, where we want to merge safe physical human-robot interaction with reactivity based on some cognitive information. And we use as a technology soft robotics in the sense of compliant devices. With respect to the objective, we are addressing safety issues, efficiency, of course robustness with respect to real-world condition, and ease of use by the end users. So the main concept gravitates around several basic topics, so going from the mechatronic part, so the design of variable impedance devices and of upper limb robot system, safety issues, indeed perception of the environment and real-time processing, task planning and replanning, being aware of the human sharing the workspace with the robot, and then interaction control, mainly physical interaction, with a series of reactive action that we have to generate in real time based on what we learned about how the robot behaves, how the human behaves when they are collaborating for a useful task. So these are the highlights. I just will present a couple of them. Certainly we want to end up with a handbook of human injury in robotics, like in the automotive industry. How safe or unsafe are these robots? The strategy for keeping safety as a primary objective, and then possibly come out with recommendation for the ongoing new safety standards. The whole consortium believes that the next generation of robot will be based on the variable impedance actuation technology, if you know what it is. The project will develop multi-freedom upper bodies, so certainly lightweight, because this reduces the possibility of injuries, compliant, but also energy efficient and as performant as conventional rigid robot arms. There are control issues based on the sensor information, but also on model base. I will detail a little bit this more recent work that we started on combined collision avoidance, detection, and reaction strategies. Of course, we have to monitor the workspaces. They may be very large, but also very cluttered in the application. We have to understand human motion intention, so really physical motion, not cognitive in this sense. We have to understand which part of the human body and which part of the robot body should collaborate, so interact physically with exchange of forces. We learn robot motion, and we have this concept of reactive action generation. So this is part of the ease of use, but also for further development of application, where you have elementary action, and I will show you some of them, and you have to decide which action to activate in real time when you deviate from a nominal plan because of some information gathered by your sensor. The nominal plan should be aware of the presence of the human, so we have a work package devoted to this, what we call safe and legible motion or task planning. So we have an IP project. This is so we are doing basic research and basic development, but we are driven by use cases. And we have 3 use cases, 2 of the industrial type. One at the robot manufacturer KUKA itself, which is also a partner. One at the AADS France on the assembly of R-plane. And another more playground, let's say, of research, which is a hospital or laboratory environment where daily activities has to be performed by a trained nurse and 1 or more manipulator arms. Starting from the basic, this is development of the variable impedance technology, and it goes through projects. So you can see on the last column what we plan to do in Safari, so upper limbs of different technology, including also variations, so we can online change the stiffness or the damping of the structure, or the whole impedance, including also a change of apparent inertia. One particular thing that I want to point out is that the group of PISA is developing a very low-cost modular variable stiffness device that can be combined with interconnection element, and it's provided to the member of the consortium, but also outside in an open hardware-software policy. So you can redesign the things by yourself or just buy the complete product, and then assembly, and you have all the documentation. The purpose is to have a community built, and if you don't know what is all about this variable stiffness, you can think about 1 degree of freedom, so a joint of robot with 2 motors, and you can simultaneously control the motion of the link, but also the stiffness of this joint. Of course, combining multi-degrees of freedom actuation of this kind, you can have changing stiffness at the end effector level or at any level in the robot structure. And this is one first assembly with this elements. This is called QMate. You can throw things. Actually, you can show that you can be much more energy efficient, and you can play drum not like Ringo Starr, but I mean, it can be also quite robust. And this is low cost, so one component of this is supposed to cost about 300 euros. And this is the high-end product. This is developed by DLRs. I don't know, you probably have seen this before. So it's human-like in size. It's compliant at all joints, including from the arm and the finger. It's quite robust. You can hit it. So it's not just safety for the human side, because it's lightweight and compliant, but it's also